Hi, it's Kate, and this is the third and final video for week 3 of Math 23B. So let's talk a little bit more about the determinants of an n by n matrix. The first thing that we're going to prove is that the determinant of the product is equal to the product of the determinants, and this proof is just a slight generalization of the one we learned last term for a 3 by 3 matrix, now just in the n by n case. Note that there's a really efficient way to calculate the determinant of A that I haven't told you yet. It is perhaps more useful than the other two. And in fact, it's my preferred method. I'm kind of at a tie between development on the first column and this method of using column reduction. And the reason for that is because when there are a lot of zeros in a matrix, usually development on the first column is really easy because a lot of the coefficients happen to be zeros. And it really oversimplifies the actual computation part of everything. But if you're dealing with a matrix that has a lot of non-zero entries, then this is the way to do it. Let's talk about column reduction. Remember that row reduction was accomplished by multiplying by elementary matrices on the left. Now column reduction is accomplished by multiplying by elementary matrices on the right. Note that if we're dealing with a matrix A that's not invertible, then its columns are going to be linearly dependent, and its determinant will be equal to 0. Now if we're dealing with a matrix A that is invertible, then there's going to be a series of column operations that if we multiply on the right by elementary matrices, we should be able to get to the identity matrix, the n by n identity matrix. And we know that the determinant of the n by n identity matrix is 1, right? That's because the determinant observes this normalization property. So if we calculate the determinant of every single elementary matrix, the product rule, this guy right up here, the fact that the determinant of the product is equal to the product of the determinants, if we're able to break down the determinant of all of these, and we know the determinant, and I mean all of the elementary operations there, and we know the determinant over here is 1, we can solve for the determinant of A itself. Fantastic. So there are 3 different types of elementary matrices, and the effect of each of these can be deduced from the properties of the determinant. Note that we can divide a column by k, which also divides the determinant by k. We can exchange 2 columns, which is going to multiply the determinant by -1. That comes from anti-symmetry. That first one comes from the linearity of the determinant. And of course we can add a multiple of one column to another, but that doesn't actually change the determinant at all. That's because of linearity and anti-symmetry. So, like I said, to calculate the determinant of A, we're going to use these column operations to column reduce it down to the identity matrix. So we start with the value of 1 for the identity matrix. We're going to multiply by k whenever we need to divide a column by k, and change the sign whenever we swap the columns. And basically what's happening is we're working backwards from the end result, which is the identity matrix, determinant 1, all the way back to what the determinant of A is. That final value is going to be equal to the determinant of A. And if we ever get a column of zeros, determinant A is going to be equal to 0. Now what's interesting here is that we can incorporate a lot of different concepts that we have already determined from earlier in 23A and see how they become relevant here. So we can look at determinant of a transpose. The determinant of A transpose is equal to the determinant of A. And that's quickly proven by a little bit of the transpose of the product rule. Remember that back in first semester, we took a look at this fact. And we had you all prove that using your fresh sigma notation matrix multiplication skills. Some of you enjoyed that more than others, I'm aware. But we can use that relevant fact and say, okay, if we have this particular matrix A and the product of the matrix A and these elementary matrices is equal to the identity matrix. Of course, this is the case where the determinant of A is not 0 and A is invertible, so it can be column reduced down to the identity matrix. We can express the identity matrix as this product of A being multiplied on the right by these column reduction operations, and we can then apply this fact and say, okay, let's take the transpose of either side. The transpose of the identity matrix is, of course, still the identity matrix, and now this multiplication on the right has turned into multiplication on the left by the transposes in the reverse order as they were up here. So now we're dealing with multiplication on the left, and since every single elementary matrix has the same determinant as its transpose, we'll go through the actual elementary matrices in class, it's going to follow that the determinant of A transpose is the same as the determinant of A. This guy on the right, that determinant is still 1. These determinants are still identical, and so the determinant of A transpose will solve for the same thing. Now, of course, you're probably already wondering, hey, wait a minute here. When I think about the transpose fact, there seems to be a connection between row reduction and column reduction, and you're absolutely correct. You can actually calculate determinants by row reduction, and that's what most people want to do. And you're free to do it because row reducing the matrix A is the same as column reducing A transpose. So if you row reduce A, you multiply together all the factors by which you divide rows, and you change the sign whenever you swap rows, you will calculate the determinant of A transpose, which is the same thing as the determinant of A. And we'll be doing a full example like this in class this week. It should be worth noting that the major thing that this whole thing hinges on is the fact that the product of the determinants is equal to the determinant of the products, and not just in the 3 by 3 case, but in the n by n case. And so that very top statement, the first statement on this page, way up here, where is it? Here we go, determinant AB equals determinant A times determinant B. That is going to be your proof, 16.1 for this week. All right, we've gotten exactly how to calculate n by n determinants out of the way, and we need to take one more step towards why they're so useful. And the important thing there is understanding their relationship to volume before we merge this into our approach of integrating things. So just hold on to that thought. We're going to get to that next week, but this week we need to talk about the physical significance of the determinant. So in 2 dimensions, we already know that a linear transformation T maps the unit square spanned by the 2 standard basis vectors into a parallelogram whose area is given by the magnitude of the determinant, or the absolute value of the determinant. And note that absolute value, a determinant can be negative, but an area cannot be, right? And in 3 dimensions, we know that a linear transformation T maps the unit cube spanned by the 3 standard basis vectors into a parallelepiped whose volume is also the absolute value of the determinant there. And this result is going to generalize to n dimensions. A linear transformation T is going to map the unit cube spanned by n standard basis vectors into a generalized parallelogram whose volume is the absolute value of the determinant of T. This is the most important thing you need to know as we move into this integration in the following week. And of course, that's actually going to be your 16.2 proof, but you'll get to that in class. We're going to break it down a little bit more clearly. Let's consider the image of the unit cube, n-dimensional unit cube, q sub n, under the linear transformation T. This image is going to be an n parallelogram, which we'll denote as follows, T acting on the unit cube. And here we have it written out as so. Note that we're going to break down the effect of T on each of the standard basis vectors. Clearly we can do that because T is a linear transformation. But we also know that we can take T and express it as a product of elementary matrices. And that's the really important part. That's the basis of understanding exactly how to prove that the volume of the resulting n parallelogram is going to be the determinant of T. Like I said earlier, we're going to go through each of the elementary matrices and talk about their effect on the unit cube. There's scaling of regions under linear transformations is what we're going to really discuss. And these are the results that rely only on elementary geometry. We don't have to go into any sort of higher level thinking, basically our notion of volume and elementary geometry. So any cube scales under T by the same factor as the unit cube. Any region scales under T by the same factor as the unit cube. And the unit cube scales under S composed of T by the product of the scaling factors for S and for T. So the rule for scaling volume means that the total result that T has on the unit cube is going to be a product of each of the individual elementary matrices whose product is T. We know that the volume scaling factor is going to be equal to the product of the volume scaling factors of the elementary matrices. We know that for each elementary matrix in the product, the volume scaling factor is going to be equal to the determinant of that elementary matrix. We're going to go through each type of elementary matrix and show that this is true in class. And since the determinant of a matrix product equals the product of the determinants, it follows that the total volume scaling factor for the matrix T is going to be equal to the determinant of T. As I said, that's going to be your proof 16.2, showing that the volume of the unit cube under the linear transformation T is equal to the absolute value of the determinant of T is the major takeaway from this half of the material this week, and will be the thing that we carry with us into next week, where we'll be going back to integration and seeing how is this relevant, when do we use it, and how does it help us integrate in other coordinate systems. As always, if you have any questions, please don't hesitate to email. And for those of you waiting with bated breath saying, what's going to happen with the determinant? Just wait until week 4. We'll be incorporating the determinant into our discussion of integration quite shortly.